This is our microvascular tension measurement system. This is the main unit of the measurement system, which can be used to control the temperature of the platform. It has 4 grooves on it, which can be used to place 4 platforms. I will now show you how to assemble a channel. This channel module can be directly removed like this. This is the main unit, and the one next to it is the air pump, and the gas can be connected here through the pipe. Look, it is connected here. It is very simple to connect. First, press down the movable fixing ring on the edge of the interface, then put the connecting pipe in, and finally loosen the fixing ring. The air pump is connected. This instrument is the physiological parameter collector. The tension sensor is connected through the communication line. Here is a waste liquid bottle, which is used to store waste liquid. The pipe of the waste liquid bottle can be connected here. Connect here, connect to the side here. Through the peristaltic pump here, after the machine is started, the waste liquid can be sucked into this waste liquid bottle. Let me introduce the source of the pump's suction liquid at this position on the mold. This port is connected in the same way as the previous port. First, press down the movable fixing ring on the edge of the interface, then put the connecting tube in, and finally loosen the fixing ring. The air pump is connected. This port is the same. Introduce the bathtub drainage, if the liquid in the bathtub needs to be discharged, through the metal pipe port above, and then through the peristaltic pump here to discharge. This green is the switch of the peristaltic pump. Push up to turn on, press down to turn off. This is the tube when supplying air or oxygen to the sample, and it is injected from here. So where is the flow rate of the air supply adjusted? Here, there is a knob on the side of the metal connection that can be turned to control the flow rate of the air. Generally, the intake airflow rate is adjusted according to the bubbles generated when exhausting and inhaling air on this side of the bathtub. In conventional experiments, the number of bubbles generated per second is generally a flow rate of about 1 bubble per second. This is the overview of the machine. Before starting the experiment, we need to connect all the wiring harnesses. Physiological parameter collector. Its communication line is directly connected to the computer via USB. Okay, let's start the experiment. Turn on the machine. The first step is to turn on the main power of the tension measurement system. After it lights up, here is the front panel operation screen, which will display the current temperature of the 4 channels. At the same time, it will display the set target temperature, which is 37 degrees Celsius by default. Of course, you can modify it manually. For example, I set it to 38 degrees Celsius now, and click Confirm. We generally set the default working temperature to 37 degrees Celsius. The button turns green. At this time, the entire thermostat starts working. The constant temperature table starts to heat up gradually. Generally speaking, it takes 1 hour to reach a stable temperature. After 1 hour, when the temperature of the thermostat is balanced, the temperature of the bath reaches the set temperature. Of course, if the bath is filled with nutrient solution or stimulation solution, the bath can keep the cells of the sample at a constant 37 degrees Celsius. The 37 degrees Celsius here depends on your setting on the front panel. After setting the temperature, we can keep the bath at a constant temperature. After the constant temperature, we proceed to the next step, which is to calibrate and zero our current tension sensor. The first step, during the calibration process, we need to put the balance on the bathtub. After placing it on the bathtub, slowly move the needle of the balance over. When the needle can touch the back of the tension sensor below, as long as it can make normal contact, it will be fine. Look here. It is enough for the needle to touch the back of the tension sensor. At the same time, it should be noted that we need to move this module to a position away from the balance so that it will not touch the balance here. The zeroing process requires us to open the acquisition software of MedLab to operate. Now we open the acquisition software on the computer. First, double-click the English version of MedLab and click to start running. At the beginning, the sampling of the tension sensors of the 4 channels will start to record data. Here, the first channel is used for tension demonstration, and the calibration balance has been placed on the tension sensor. The current mode is General, and we need to change the mode to Tension Sensor first. Click Setting in the upper right corner. Remember, this must be set after running the machine first. General needs to be modified here. Click. Select the second item, Tension Force, and select MN for the unit. Then select the first General here, and after confirmation, click OK. After setting the parameters, look at the interface on the right. Currently, a value of 2.5 mN is displayed here, and we need to calibrate and zero. Click Setting and select the second option, Baseline Setting, to zero the baseline. After zeroing, the baseline will return to 0. Next, we use weights to calibrate. This is a 2-gram weight, and we put it on the scale. You can see the change in the value. At present, this weight makes the baseline on the interface change very little. You can zoom in through the Zoom Out here. Enlarge the baseline. Here is an example. The enlargement is a bit large. We reduce a little. At this time, the right side shows 1.7 mN or 1.8 mN, because it has not been calibrated, so the displayed number is incorrect. Now demonstrate the calibration method. Click Setting, then click the 4th Calibration. The current value is 1.83 mN, and we are using a 2-gram weight, which corresponds to 20 mN. Enter 20. The machine will automatically calculate the calibration coefficient. Now you can see on the right that the tension is 19.89 mN. Calibration is complete. We can take off the weight. Here we only use the first channel as a demonstration dot. If the other 2, 3, and 4 channels need to be used, calibrate them in the same way. Next, we will demonstrate how to create a new experiment. Reopen the English version of MedLab, and then there are items to enter, including experiment name, experimenter, experiment date, and conditions. You can set it according to your needs. Now suppose our sample is connected to the first channel. First, measure it and click Setting. If the calibration is complete, you can select Setting here, and then select Tension Force in this option. Select 30 grams for type, and General for data analysis. You can modify the unit here. Currently, mN is used. You can modify it to gram or kilogram. If there is no mN in the drop-down option, you can select it with the mouse and manually enter the unit mN. Click OK to start the experiment. At this time, the setting is modified. Click the lower right corner to start measuring. In the normal measurement process, a preset tensile value will be pulled. I will demonstrate it here. For example, now I put something into the bath, and the preset tensile. Tension is 2.9. N, when the preset tensile tension is 2.9. N, comma, we need to conduct a tension experiment. I add a tension to it by sliding slowly. Of course, my simulation may be less stable for the measurement of this tension. If you want the machine to collect slower, you can adjust the speed of the recording time through the second window on the right. This is the tension setting. During the recording process, if you mark something relative to something, you can mark it to record. There is a button for marking and recording, which we can use to add a start tag to the timestamp. Click to add, and the star mark on the baseline will appear. For example, we want to add a stimulus solution, such as potassium chloride. Then click here to add a label. Generally, after potassium chloride is added, a pulling force will be generated. By adding a label, the waveform after the addition can be recorded. When analyzing experimental data, we can measure through the selection box. For example, I click the lower right corner now to pause the experiment. We can select this label area through the selection box, and it will get the maximum value, minimum value, peak value, and average value of this section of data. This is the maximum and minimum tension values in this section of the selection box. We measure the tension of isolated microvessels to evaluate the relaxation degree of the sample under the tension of the stimulating fluid. We need to know the optimal pre-tension of the untreated sample first. So how do we know the optimal pre-tension? We can use MATLAB to measure the approximate preset tension. For the measurement of the optimal pre-tension, we have another special program called normalization. Double-click to open the program on the desktop. This program is bilingual. Click here to switch to the English version. We need to fill in the following items. The first one is to fill in the diameter of the tungsten wire. The diameter of the tungsten wire used in our experiment is 40 microns. Then fill in the length of the blood vessel, assuming that the blood vessel length is 2 millimeters. There is an experience value option for IC1 compared IC100. Generally, its experience value is different depending on different experimental subjects or different tissue parts. The commonly used value is 0.9, so we fill in 0.9. The target pressure we plan is 13.3 kPa. We start to fill in the experimental data of each time to speculate. The first column of the table filled with data is the moving distance of the micrometer on the mold. The second column is the passive tension, in Mn. After filling in, the pressure will be automatically converted. Now we will input the simulated data, and we will simulate the input with the data of an experiment of DMT. Now open the DMT document, which is the experimental document of DMT. Compare the document and fill in the first column of data first. In the first column, when the micrometer moves 0, its passive tension is 0.324 mn. At this time, the passive tension is actually the initial zero value of the sample measured by the tension sensor itself. If the passive tension is 0 when the micrometer is 0, just fill in 0. We are now displaying according to the DMT data. Fill in the passive tension of 0.324 and click OK. Now add the second point. The second point is 80 micrometers. At 80 microns, its tension is 0.558. Click the plus sign next to Operation here. Add 80 microns, and the tension value is 0.558. At this time, the software will automatically convert the pressure at this time. We start to fill in the data of 130, 180, and 231 by 1. The tension of 130 microns is 0.783. The passive tension of 180 microns is 1.167. At 230 microns, 1.774 is measured. The current pressure is 3.42 kPa. You can see that the coordinate graph here will automatically connect after adding multiple points. Because our target pressure intensity is 13.3 kPa, once the displayed predicted pressure exceeds 13.3 kPa, we don't need to add any more data. That is, when the pressure reaches 13.3 kPa, the IC100 value can be found. Let's continue to add the DMT data to the table. At 280 microns, the tension is 2.768. 330 microns is 4.348. (380 microns is 7.223, and the converted pressure value is 11.2. It is already close to the target pressure value of 13.3, so add another data. The passive tension of 430 microns is 11.1. Okay, at this time, the predicted pressure exceeds 13.3 because the software has found that it exceeds the target pressure by 13.3 kilopascals. In the coordinate graph, this calculated pressure line will be compared with the isobaric line at one point. Then this point is the position corresponding to IC100. It is 1015.5 microns. This is the circumference of IC100, because we have previously filled in the empirical number of IC1 compare IC100, which is 0.9. Then the software will automatically convert the value of IC1 to 914 microns. The software can calculate the micrometer corresponding to the optimal pre-tension based on the coefficient is 354 microns. At present, when we are experimenting, it has moved to a position of 434 microns. We need to start to move the micrometer back. After moving back to 354 microns, the optimal pre-tension position is reached, and then the following relaxation or compression stimulation can be started. To detect the relaxation and compression tension amplitude of the sample itself, and conduct subsequent evaluation of the experimental results. This is the software for normalization calculation of the optimal preset tension.